Hello everyone. Today we will be working on sampling distribution. By the name of it, we will be working on sample and then there will be a distribution. So how we'll get a distribution using some sample, we will try to look at those. And we will also try to see how we can find the distribution of samples, but then again, what's the statistics? Previously we looked at statistics is all about the characteristics. We are trying to make inference about the population parameter, right? So we look at those previously, but today we will try to look at sampling distribution of the statistics. The statistics could be the means, or if we have two groups, then what's the difference between those two means from those two groups? How about the proportion? Proportion is also a statistics. And then if we have two proportions, that means from two groups, if we have two proportions, whether we can make a sampling distribution of the difference between those proportions. Same thing, difference between those means. And then how about the distribution of variance? Many times we talked about means, but how about the variance? Also the ratio, that means if we have a group and then if we have two groups, then we can also take a ratio of those variances in those groups, and whether we can make a sampling distribution. We'll also look at the tables, because previously we used Z table, and then since we are talking about distribution, we will try to see which distribution it follows, the data follows, and then what kind of table, the critical table we will be using. Based on the distribution, we will select that. That's our goal. So if you look at the commentary, let's go to the commentary page. Next. So you will see that we listed them. So we try to list the parameter. So parameters are coming from population, and then statistics is coming from sample. So you can see the symbols are different based on population, based on sample. So if we are talking about just one mean, that means let's say we have a group of people, let's say we are talking about income or in Canada, all eligible people who are working, the working group. And then if we are talking about what's the mean of that population, that means in Canada the mean income of people, then we can say this is just one group. If we have two groups, let's say people age more than 50, people age less than 50, we have two groups. That means difference between two groups, we can find another distribution. And if we are talking about sample, then you can see if we take sample in Canada, so try to see whether taking all people who are in the working group, we can take some sample and we can try to find their mean. Then the symbol changes to the sample. You can see we are using the X bar, but for the population we are using mu. That means we also try to use the variables. So if you use variable X, then you can say I'm going to use this symbol, or you can use variable Y if you want, or variable Z. Whenever we are talking about proportion, let's say what's the proportion of mountain pine beetle in Canada, let's say not in Canada, let's say only in British Columbia. So what's the proportion of mountain pine beetle based on let's say the trees. We could have two kind of trees, one is infected, another is not infected. So what's the proportion of them? Then you can see we are using a hat on top of the proportion where we are talking about sample. Same thing if we are interested to find the distribution of difference between two proportions, then we can take the difference, and then in the sample we have to say that we are taking the sample and taking the difference between them and making a distribution. Same thing for difference between paired observation, and then we can also talk about the variance. We can also talk about the ratio of variances. So I'll show you how the sampling distribution works. Let's give you an example. Then it might be easier for you to go through the sampling distribution process. So let's say this is in a forested area, and then in this forested area, if we know information or measurement of all trees, then we have the population information. Then we can find what might be the population mean height, since we have the information of all trees. If you take a sample, let's say I take a sample of 35 trees from this forested area. Randomly we take that. Then we calculated their mean of all these 35 trees, the sample trees. And we found a mean 8.1 meters maybe. If I take a new sample of size 35, not these trees, we don't know whether these trees will be selected or not, would we get the same sample mean? Maybe, maybe not, right? We are not sure. So then we need to talk about three types of distribution in there. So you can see, if we have the information of all trees in this forested area, then we can easily find a histogram. So you can draw a histogram using let's say if you have groups of all those, the data set, if you develop a group, then you can see that in each of those groups how many trees you have, and then what's the height of those trees, because height is our concern in here. Height is our variable in here. And then we calculate that population mean height in this population is 6.99 meter. So you can see the red one is the mean. And then we have the, in our x-axis we have the height in meters, and then in each of those intervals, then what's the percentage. You can see it's between 0 and 1, so you can say 5%, 10%, or something like that. Then I take a sample, and then I took 7 samples. That means 7 sample trees are selected randomly, and then I found their sample mean. Sample mean is 5.9. Since the sample size is really small, then it is difficult to create a distribution, but you have some idea what might be the distribution. Then I take it, the mean I found, I separated it, and then I saved it here. Then I did the same thing. That means again I took 7 trees, and randomly I chose that sample, and then I found the mean of those sample trees. I did the same mean of those sample trees. I saved their means. That means what I'm trying to do in here is that I'm trying to see if I collect the means of those samples, and then whether I can create a distribution from there. So this is where we have the sampling distribution. A sampling distribution of what? Sampling distribution of the mean. If I was talking about variance, if I was talking about proportion, then that will be sampling distribution of variance or sampling distribution of the proportion. And if I'm talking about, let's say, making the difference between 2 groups, population 1, population 2, and then take the samples from population 1 or population 2, if I take the difference between them, the mean difference between them, then I would again get a distribution from there. So that's what we are calling the sampling distribution when we use the samples. Whenever we use the statistics, that means the mean is the statistics in here, then we are saying that this is the sampling distribution of the sample mean. So in the distribution, what happens is that you saw that we have the sampling distribution, and then in the sampling distribution, the standard error, where is it coming from? So I talked about it before. Whenever we have the statistics, and then in that statistics, using that statistics, if we try to find the sampling distribution by taking it again and again, then let's say we are talking about the mean. Let's actually draw them. That might be easier for you to understand. So we were trying to see if we take all the means, that means the mean we were trying to get many times, and we try to find the distribution of mean. So you have to think about, we are no longer talking about the variable itself. Variable is x, but every time, since we are taking the mean and we found the sampling distribution of mean, then sample set to sample set, or the, let's say, the how much variation we have in these means, that means you can see the variability within our data set. Well, how much variability we have. So that's what we have, the standard error of mean. Because if we are talking about a variable, if we have a distribution of a variable, let's say x is the variable and then distribution of a variable, then we are saying that this is the variance, or this is the standard deviation. But in here, we're not talking about the variance or standard deviation. Whenever we have the variability of those means, then we have the standard error of mean. We cannot call them standard deviation of mean. That's the standard error of mean, because we are talking about sampling distribution, not just a variable. Okay, let's clear. So in the normal distribution, that means normal sampling distribution, so whenever we are talking about mean, if we are taking the mean many times, then you will see that we are getting the normal distribution, that means bell-shaped distribution. I showed you before, and we have two parameters, mean and variance, and we can standardize them. So you can see that we are talking about the variable, the variable value y, and then statistics is the y is the statistics in here, and then we can actually standardize them. So I'm basically interested to talk about the sampling distribution of means and proportion. So you can see that we are talking about central limit theorem. So let's talk about the central limit theorem first. So using the central limit theorem, we can talk about the what are the characteristics of those sampling distribution. So let's say let's actually draw that. So what's the central limit theorem says is that if we have, let's say, if we have a population and we have the population distribution, but then again, whenever we take the means many times, this is the let's say this is the for the population, and this is the population mean. And if we take the samples many times, and then you use the sample mean that I just showed you the example, then you will see that if we repeat that many times, then you will find that the population mean that you will find in the population will be exactly same what we have in the sample. So that means the sampling distribution, the mean of those mean is same as what we have in the population. So whenever we actually have a larger sample, so let's say 30 or more, then even if our distribution in the population is not normal, let's say skewed, if we take samples many times, if we repeat that, And if we take larger sample size, let's say 30 or more every time, then in the sampling distribution you will see that it's actually normal. So that means that's the central limit theorem says, even if our population was not normal, that means was not bell-shaped, but since we are taking samples many times and the sample size is large, 30 or more, then it's actually a bell-shaped. That means a normal distribution. So that's why we are talking about central limit theorem first. So using that theorem, we can actually try to find, let's say we have a sample mean, or we have difference between two sample means, or we have differences. Actually, let's say we are trying to make the differences, or proportion, difference between proportion. We can have any of those statistics. So you have to be careful which statistics you are talking about. If we are talking about mean, then mean of those sampling distribution is same as the population mean. Let me give you an example. Why is that? Only just a really small sample, small population, 0 to 4. These are the only three values we have in a population. Let's think about that. Sample size is the population size is 3. Then we found that mean of those three values in the population is 2, and the standard deviation of these three values is 1.63. Then we'll take a sample of size 2, small sample, from this population. That means population we have 0 to 4, and then we took randomly 2 samples, and then we take the mean of these 2 samples, which is 1. Then we try to take all possible combinations. We're not taking it randomly, all possible combinations we took. So you can see that there will be 9 possible combinations. Using those 9 possible combinations, what we try to see is that if we create a table, so we say that every time it will be the possibility of each of those combinations is 1/9, and then we try to find the mean of those possibilities, all those possibilities. So you can see I just multiplied what's the mean and then what's the possibility. Possibility is always same. So I find that the mean I found is exactly same as the population mean. That means we took all possible combinations and we found the mean is exactly the same. So you can see mean of this population is exactly same as the sampling distribution mean in here. And then you can see that we are talking about variability, how much variability we have. So in terms of variability, since we say that in the sampling distribution we will talk about standard error of mean, it's no longer the standard deviation. So we will try to take the this is the equation we are going to use. So that means you actually saw that when you worked on the group data. If I found the mean, the variability, and I found the variability, there is a relationship between the population data and then the standard error of mean. That means if we know the population variance, population standard deviation, divide by the square root of the sample size. Each time the sample size we took 2. Then you will see that it's exactly this is actually the exactly the same as the standard error of mean. That is, if we know the population standard deviation, divide by square root of how many sample size you took every time, then it's actually our standard error. So that means the standard of the sample mean is equal to the population standard deviation. So you will see that if we increase the sample size every time, instead of taking 2, if we take sample size a little bit more larger, then the variability you have will be less. If we have sample size 30 or more, then you will see that distribution will be normal. So that's what I would like to talk to you about in here. So you can see that whenever we try to find the sampling distribution of the mean, then you will see that you can connect them. So we are basically talking about this one. Let me actually draw them. That might be easier for you to understand. Okay, so I was talking about this part, that means only single mean. So we have the standard error of mean if we are talking about only one population, and then we have the population mean and then sampling distribution of mean, and then we have the standard error of mean is sigma divided by root over n. So sigma, mean, they are actually from the population. Be careful about that. The sigma, that means the population standard deviation. Population standard deviation, if we know that, if you actually divide it by square root of sample size, then you will find the standard error of mean. And then if you are talking about two of them, that means two population, then you will see that the combined standard error would be the combination of them. That means you can think about just keeping them inside and then taking the square root of them together. You can write down in your cheat sheet so that you can use it in your exam. So if we are talking about difference between the means, so you can see that instead of showing it this way, we are basically taking the difference between them. Then it will be like that. Same thing for proportion, and then you can see the difference between the proportion. So you can see whenever we have the larger sample size, more than 30, in many books you will see that it's not more than 30, it might be 50 or 100, then it will approximately normal curve. That means the bell-shaped curve it will create. And then we talked about in central limit theorem, I just said to you, even if the population is not normal, then if you take the sampling distribution, you will see that they are creating a normal distribution if the sample size is large. That's what we have in the central limit theorem. Okay. And then sampling distribution of mean, I just showed you was the sampling distribution of mean in the slide. So in the, let's actually clear the screen. Okay, so we can standardize them, and then we can take the mean in the sample size, what is in the population, and then using the sampling distribution of mean using the central limit theorem, we can say this one. So sometimes you will see that we are making some adjustment. So if it is without replacement, then you can see in the without replacement, we have to add an adjustment on the standard error of mean. So if you see that if it's with replacement, then you can see it's just the sigma divided by root over n. But whenever it's without replacement, and then we have the sample size are drawn from the population is finite. Finite means we can count them. That means it's actually we have to add an adjustment factor. So many times you will see that instead of z, we are talking about t distribution. So when you will see that sample size is small, and then the mean and standard deviation, basically the variance, we don't know the variance of the population. That means we have to use the sample variance because we do not know what's in the population. In that case, we cannot use the z distribution. We have to use the t distribution. That means we do not know what's the population standard deviation, and then the sample size is small. Then instead of the z statistics, we have to use t. in T, you have to use the degrees of freedom. That means sample size minus 1. How many observation we have is free of the statistics. Then we can say that the degrees of freedom we have to use is the sample size minus 1. It looks similar to Z, so you can see the sample mean minus the population mean, and then standard error from the sample, and then square root of n. So this part, the middle, the bottom area, we have the standard error of mean. If we look at the T table, you will see that we are reading the T table a little bit differently. So let me show you. Okay, so you can see that in the T distribution, we are talking about what's the sample size minus 1, and then over here we have the distribution. So let's say we are talking about T distribution, and the T distribution is also, you can see they are bell shaped. That means both sides we can see that they are the probability would be the same. So let's say if the degrees of freedom is 9, then within the 95, that means less than, let's say, 95, the area we have for this area, that means 0.95. In this area 0.95, the value of the critical value in here would be 1.83. So based on what's the degrees of freedom we have, so you can always find in the distribution what would be the critical value. So critical values are inside, and then the probabilities are here. Okay. Okay, so that's how we can find the critical value. Whenever we have the sample size gets larger, so you will see that whenever sample size gets larger, so you will see that these values, if you look at the Z table, then you will see that these T values exactly same as in what we have for these probabilities in the Z table. That means if we have larger sample size, then the T and Z, the critical values, will be exactly the same. Okay, so in the next video I'll be talking about other distributions. I hope you enjoyed this one, and then try to look at the chapters, the examples we have in the sampling distribution chapters in the textbook, and it will be easier for you. Okay, thank you.